Hello and welcome to our series on 3-dimension geometry. In our previous lessons, we talked about line in space. Today, we will discuss equations of plane. Plane, as the literal meaning of the word goes, suggests something which is smooth, and that is how we define plane in more technical language as well. We say that a plane is nothing but a flat surface on which a straight line joining any 2 points on it would wholly lie. And we are looking at finding the equations of the plane, which will be uniquely determined if any one of the following is known. The first one is if I know the normal to the plane and its distance from the origin. Now, normal to the plane is nothing but a direction, in our language a vector, which is perpendicular to the plane. So, if I know the normal and I know the distance of the origin from the plane, then we are looking at a possibility of finding the equation of the plane. The other possibility would be if I know a point on the plane and the normal to the plane. Third possibility would be if I know 3 non-collinear points through which the plane passes. Now, each of these would give rise to the equation of the plane that we are getting ready to learn. Starting off with the first one, equation of plane in normal form. When we are given the perpendicular distance of origin from plane, say the distance d, and we are given a normal vector. So, we know the vector which is perpendicular to the plane. So, if I take ON to be the perpendicular from origin to the plane, then the distance ON is small d and the vector ON is in the same direction as the vector n that is given to us. Therefore, vector ON will be d times the unit vector along the direction of the vector n. If I take P to be any point on this plane with position vector r, then I know that the vector ON, which is perpendicular to the plane, will also be perpendicular to the vector NP that is contained in the plane. And therefore, the dot product condition, that is the dot product of these two vectors equal to 0 must be satisfied. So, you do get d n cap dot r vector minus d n cap equal to 0. As we simplify this, I get r dot n cap equal to d, and this is what is known as the vector equation of plane in normal form. Also, as I rewrite this using the vector r as xi cap plus yj cap plus zk cap and n cap as li cap plus mj cap plus nk cap, where L, M, N are direction cosines of vector n cap. N cap, remember, is a unit vector. This gets rewritten as Lx plus My plus Nz equal to d. So, that becomes the Cartesian equation of plane in normal form. Now, what we have to note here is that if the two equations, that is r dot n cap equal to d, had an unit vector, and in place of a unit vector I have, say, a vector n known to us, and we have an equation given as r dot vector n equal to d, then the Cartesian equation of the plane would translate as Ax plus By plus Cz equal to d. Then A, B, C, that is the coefficients of x, y, z, are the direction ratios of the normal to the plane. Another possibility is if I know the point through which the plane passes and I know a vector which is perpendicular to the plane. The normal form depends on knowing the distance of origin from the plane, which is not always available. So, this form, that is where I have a point given and a normal, is going to be most frequently used form. So, how does it affect the equation of the plane? Starting with, if I look at the figure, then I know the position vector of the point A, say the vector A with coordinates x1, y1, z1 known. I know the normal to the plane. So, vector n, in this case symbolically represented here as touching the plane, is not necessarily to be there. It is just a direction which is perpendicular to the plane that is known to us. So, that vector n has direction ratios as a, b and c. If I take P to be any point on this plane whose locus has to be formed, then we know that the vector AP is perpendicular to the normal, that is the vector n. So, the dot product of vector AP and vector n must be 0. So, vector r minus vector A dot vector n must be equal to 0, and that gives rise to what is known as the vector equation of the plane. You may simplify this further and write as vector r dot vector n equal to vector A dot n, but it is perfectly fine to look at it like this as well. Rewriting this in Cartesians, it will turn out to be same as A times x minus x1 plus b times y minus y1 plus c times z minus z1 equal to 0. And therefore, that becomes the Cartesian equation of plane passing through the point x1, y1, z1, having normal with direction ratios a, b and c. If we revisit the two things that we have discussed so far, vector form of equation of the plane is given as vector r dot vector n equal to d. Now, vector n is a normal to the plane and d is that quantity that would simplify if you find vector A dot vector n. In Cartesian, after simplification, the equation of the plane in general will always simplify down to a linear equation in x, y and z in the form ax plus by plus cz plus d equal to 0. I have chosen capital D with an understanding of taking it a little different from the d earlier. Otherwise, any constants a, b, c and d as in that sense will be the required, and a, b, c, that is the coefficients of x, y and z, will define the direction ratios of the normal to the plane. I think we are now ready to look at the third possibility. What if I have 3 points, non-collinear points, through which the plane is passing? Instead of giving you a general formula for that, let us just take a question where you have to form equation of the plane which is passing through 3 non-collinear points, and let us see what the method is and what kind of a equation I get at the end of it. The problem here states that find the vector and Cartesian equation of the plane passing through the points A with coordinates 1, -2, 5, B 0, -5, -1, C -3, 5 and 0. Now, if we try to make a picture as shown here, things will become easier to follow. If you take 3 points on the plane, say as marked here A, B and C, then we know, since by the definition and the characteristic of the plane, the vector AB and the vector AC will completely lie on this plane. And so, the direction which is the normal, which is much required to find equation of the plane, the direction of the normal will always be perpendicular to the vector AB and the vector AC both. That is what will work as a key result and a concept. Let us begin with taking that vector n to be parallel to the cross product of vector AB and vector AC. Since vector algebra taught you that cross product of any two vector is always parallel to the given two vectors. and therefore, if I find the vector AB as position vector of point B minus position vector of point A, find position vector of C minus position vector of A to get vector AC, then find the cross product using determinant, I get the vector AB cross vector AC to be 57 times I cap plus 19 j cap minus 19 k cap. So, normal is any direction which is perpendicular to the plane containing these 3 points, and therefore, normal will be same as the vector AB cross AC. We did see that equation of a plane through a point is given as vector r minus vector A dot n. Now, vector n gets replaced with AB cross AC. So, we have everything ready to form equation of the plane, and that simplifies to be same as vector r dot 57I plus 19j minus 19k cap equal to negative 76, simplification of vector A and the vector n which is along AB cross AC dot product, and therefore, simplification gives us the final answer as vector r dot 3I plus j cap minus k cap equal to negative 4 as the required equation. To rewrite this in the Cartesian form, all you have to do is replace vector r with xi cap plus yj cap plus zk cap, and the dot product will give me 3x plus y minus z equal to negative 4, which I can rewrite and simplify as 3x plus y minus z plus 4 equal to 0, and that is the required Cartesian equation of the plane. So, the 3 forms that we discussed today, one starting with the normal form where we need the distance of origin from the plane, another form where we had a point known and direction which is normal to the plane, third case where we had 3 points known, non-collinear points. Now, suppose these 3 non-collinear points were special points, special as in terms of they are nothing but coming out as points where the plane touches the 3 axes. That is what comes out as the intercept form of the equation of plane. Let us take a look at how and what special form does it result in. Here we have a plane making intercepts A, B and C units on x, y and z axis respectively. So, the plane must meet the 3 axes at the point A 0 0, 0 B 0 and 0 0 C respectively. Now, in this case again you can use the same procedure as in our previous question, because these are 3 non-collinear points. But just to get that special form, if I take Cartesian equation of plane as Ax plus By plus Cz plus D equal to 0, then I know that A comma 0 lies on this plane. So, if I replace x, y, z with these coordinates, I get a condition which tells me that capital A is equal to negative d upon small a. Similarly, you get capital B as negative d upon small b and capital C as negative d upon small c. If I use these values of A, B and C in the assumption of the equation of plane as Ax plus By plus Cz plus D equal to 0, and I just rearrange the coefficients, I will get a special equation in the form x by A plus y by B plus z by C equal to 1, which is known as the equation of plane in the intercept form. Equation which is very similar to intercept form of line in 2 dimension, but here we have a z by C added in. So, it becomes a linear equation in x, y and z represents a plane. This is a special form which is to be used only if you know something about the intercepts. Otherwise, we depend on the point and the normal form. Today's lesson focused on equation of plane in vector and Cartesian form, and we covered several forms, but there is still a whole lot to learn which will be covered in our future lessons. I hope you will be there to watch them. All the best till then.